It's a pleasure to have Debdeep give a talk to us today. I actually would have liked to have him in person, but unfortunately, the circumstances don't allow yet. But Debdeep is my academic brother. We were both students of David Thompson at Duke. So I think I left the year that Debdeep joined or around there. He was first an assistant professor at the University of Florida between 2012 and 2017, and he's currently, since 2017, he's been at Texas A&M University at College Station. And he's going to give a very interesting talk about theoretical and algorithmic foundations of variational inference. So many of you may be familiar with variational algorithms, particularly in the Bayesian context. And the theory of those algorithms has been a little bit of an elusive topic. So Debdeep is one of the people that has been working on trying to put those algorithms into a sounder foundation. So again, it is a pleasure to have you, Debdeep, and welcome.
Thanks, Abel, and thanks, Yenchi and Abel, for the invitation. It's a pleasure to be speaking at this. So I'll be talking about some of our recent ventures into understanding some of the theoretical foundations of variational inference, in particular, when it works and when it does not. So variational inference has been increasingly popular, particularly from an empirical standpoint over the last 2 decades or so. But there has been a major lack of understanding, as Abel pointed out, regarding the statistical and algorithmic properties of variational inference. So my research over the last three to 4 years has been to trying to understand some of the properties of variational inference and its extensions. Although I must admit at this point, we are just barely able to scratch the surface of the problem. And of course, there are many more interesting problems that are left unanswered at this point. So, so this is a joint work with my colleague Anirban Bhattacharya and Yoon Yang, who is currently at UIUC. A couple of students are involved, Sean Plummer and Hongyang Wen. So since I'll be focusing mostly on the Bayesian framework, let me quickly set up some notations. So we collect the observables y1 through yn in this vector y superscript n, and the hidden variables or the unknown parameters are stacked up in this vector w superscript n, which is theta and zn. So theta is a parameter of interest, and zn, z1 through zn, is the collection of latent variables. So you can imagine in a Gaussian mixture model, theta might represent the cluster-specific component parameters, and CNs are basically the cluster allocations. So a statistical model is formulated by first specifying the observed data likelihood function, which is the distribution of the observations y given the z's and the thetas, and then specifying the latent variable distribution. So a Bayesian inference proceeds by setting up the prior and extracting the posterior of the parameters as well as the latent variables using the Bayes formula. As most of you know, much of the computational problems that stem in variational or Bayesian inference in general is from the intractability of the normalizing constant of the posterior, beyond simple parametric models or low dimensional problems where you can numerically integrate. So of course, Markov chain Monte Carlo over the last 30 years has been incredibly popular in avoiding to compute the denominator and use sampling-based approaches to sample observations from the posterior distribution. But it's known to have mixing and some scalability issues for large data sets. So in order to mitigate this problem, there has been a development in approximate Bayes inference, starting with numerical integration, of course, but then kind of diversifying to Laplace approximation, more recently to expectation propagation and variational inference. So variational inference dates back to as early as Feynman's work in 1972, and then to the literature of calculus of variation in the 1980s. and David Mackay's work and Hinton's work back in the 90s. So the idea is fairly straightforward. I think most of you actually know. We start with a pre-specified family of distribution on the parameter space and the space of latent variables. And then we approximate the posterior by a closest member from this tractable family in the sense of Kullback-Leibler divergence. So basically what we do, we look for the best possible approximation to the posterior within this family where the divergence is measured in terms of the KL divergence. And we call the arg min of the scale divergence, the minima, to be Q hat. Okay. So of course, the success of variational inference, I do not have to stress too much, and this has been nicely captured by this poster that Andy Gelman and Aki Vetteri posted recently on the web, and I just stole from there. So variational inference features as one of the top statistical ideas of the past 50 years, and it features as the number 5 in the sense of generic computational algorithms. So again, just to kind of impress on you the applicability and success of variational inference, if you simply run a topic model on the corpus of NIP's 2015 accepted papers with 5 different topics, then you are going to see that the word variational features in the top 20 words in one of these topics. So it's quite popular. So just going back to our topic, a quick way to see why variational inference can avoid computing the normalizing constant in the posterior is through this very, very simple identity where we decompose the log marginal likelihood in terms of a quantity which we call as the evidence lower bound plus the Kullback-Leibler divergence that we are trying to minimize. So as the left-hand side is independent of the parameter Q, minimizing the Kullback-Leibler divergence is equivalent to the maximization problem of the evidence lower bound. And you can see that there is no normalizing constant in this evidence log. Okay, so this is quite easy to see. Basically, the 2 outstanding questions of interest when it comes to variational inference is the first one is statistical accuracy type of analysis, and the second one is computational guarantee. So the first question is whether the Q theta hat that you get out of this minimization problem is really a good proxy for the posterior distribution or not. Or just to put more simply, whether this Q theta hat really inherits some of the good frequentist properties of the posterior. And we have been able to address some of these questions in the papers that I have mentioned. From a computational side of things, obtaining this minimizer is typically a hard non-convex optimization problem. And it really is not guaranteed whether the Q theta initialization that you start with really converges to the arg min. It's only recently been known in very special cases in the context of stochastic block model and Ising type models, but a general theory is missing in the literature. Okay, so the choice of the variational family is really critical. That kind of balances the statistical accuracy and the algorithmic convergence properties. One of the most commonly used variational family is the mean field approximation, which considers all joint distribution over the d-dimensional parameter that factorizes. That means we simply assume that in the that the approximator has theta 1, theta 2, theta d. These are all treated independently. So one can even obtain a parametric approximation to the posterior. So we can simply restrict our family to be a member of the exponential family. More recently, expressive variational distribution in terms of variational autoencoders, mixtures of Gaussian, variational boosting are being proposed, which are really powerful and can approximate the entire posterior distribution pretty well. But our talk would be primarily restricted to simple type of approximation because we know that computation is really feasible with those family. So what kind of theoretical properties do you really expect? Okay, so let's come to the first part of the talk, which is the statistical accuracy. So typically, we do not expect to capture the entire probability distribution really well, entire posterior distribution really well, if you're doing, let's say, a mean field approximation. So the spread of the variational distribution is typically small compared to the posterior, but variational Bayes is mostly used to obtain point estimates. So the question is whether there is any loss in statistical accuracy in terms of convergence rates of these point estimates. Are they kind of similar in performance with the true posterior mean, for instance? So on the computational side of things, as I mentioned, typically, if you're doing a mean field approximation, it's a non-convex optimization problem. Does it really converge? So the posterior correlation between parameters, does it really play any role? Does the initialization has anything to do with the convergence? Things like that we're wanting to address in this talk. Okay, so here is a toy illustration of variational inference in case you are not familiar with it and how it works. So we are running a variational inference with spike and slab prior on a high dimensional regression with 100 samples and 200 predictors, and the data is generated from a linear regression model with Gaussian errors. The true coefficient vector is sparse in the sense that only the first 5 entries are non-zero and the rest of them are 0. And this is shown in this black line. So the variational estimate, the initial variational estimate, initialization is shown in this red curve. It's basically initialized to all 0.25, let's say. So this is iteration 1, and iteration 2, we can see the red dots for the first 5 coordinates starts to converge to the corresponding true values, while for the noise variables, they are starting to converge to 0. We run that chain long enough, and finally, at iteration 5, there seems to be not much improvement from iteration 4. That means we have convergence. Now, we want to make sure in this talk whether the estimates that we are obtaining here are really statistically optimal in a sense, whether the closeness between the red and black dots can be argued from a statistical point of view. And also we would want to address that what kind of initialization that we want to perform so that we can converge to the global optimum. Okay. So let's come to the first part. So again, throughout this talk, we'll be working with an oversimplified setting. That means we won't be working with the original likelihood per se. So we'll be working with a modified likelihood where we raise the likelihood to a fractional power. So there are philosophical reasons of doing that, which I'm not going to get into, but our main goal is to simplify the theory as much as possible for the sake of this presentation. Everything carries over to alpha equals 1, but the fraction is 1, that means to the original likelihood. So when alpha is strictly less than 1, it's really, the theory is really simple and easy to describe. That's why we kind of adopt that particular convention here. Okay, so let's forget about variational inference for the time being. Let's try to first analyze the fractional posterior, and let's try to see what kind of condition we need for the fractional posterior to be converging to the true parameter. So script ln theta is the log likelihood. Script ln theta theta star is the ratio of the log likelihood, where theta star is the true parameter. So the fractional posterior can be written as e to the alpha times ln theta theta star pi theta, and then we have to normalize it to make it a valid density. Okay. So now why a fractional posterior is going to converge to the true parameter? So of course the denominator can be lower bounded if the prior charges positive probability around small neighborhoods of the true parameter. So we can have the denominator to be not too small. But let's look at the numerator. If we can make the numerator to be small once theta diverges from theta star, then we can have posterior consistency. Basically, we can allow the posterior to concentrate around theta star. Okay? Now, this is quite easy to see if we work with this fractional posterior setting, because if you take an expectation of just the alpha times log likelihood e raised to the alpha times log likelihood, you can see that we would simply get an affinity term. This is called the Renyi affinity of order alpha. So for alpha equals 1/2, you'll get the Hellinger affinity, which is pretty common. Now, you can actually define a divergence through this affinity by taking 1/α-1 log of this affinity. So since alpha is negative, this is going to be positive because the affinity is always in between 0 to 1. So it's easy to see that the expectation of the numerator, of course, without the prior term, we are ignoring the prior at this moment, is simply e raised to a divergence here. So as you can see, if theta goes away further from theta star, the numerator is going to go to 0 exponentially fast. Okay, and we can always lower bound the denominator because the denominator is an integral over the entire parameter space, and this will actually force the posterior to concentrate. So just to have an idea of what kind of divergence this Renyi divergence is, if you just take Renyi divergence of order 1/2, it has this very simple relation with the Hellinger distance, and locally this quantity is equivalent to the Hellinger distance because negative log 1 minus x is like x. So just a couple of simple examples. For Gaussian likelihoods, the Renyi divergence is equivalent to the Euclidean distance. So there is not much loss in terms of interpretation. Now, the following variational characterization is really important to understand or develop risk bounds to the posterior distribution. So let's look at this very simple variational characterization. So the Kullback-Leibler divergence between any arbitrary probability measure Q and the posterior distribution can be written in terms of a penalized loss, which is the first two terms in here, plus the log marginal likelihood. Okay? So now this penalized loss kind of looks like the negative ELBO if you get rid of the alpha. So this looks kind of like the ELBO if alpha equals 1. Now, here is a variational characterization. If we try to minimize this objective function of the penalized loss function with respect to Q, and if your minimization is unrestricted over all probabilities which are absolutely continuous with respect to the prior, you can actually show that this quantity is going to be minimized at the posterior. And this is pretty easy to see because then the KL divergence would be exactly 0. Okay, and this is essentially the basis of our result. So first, what I'm going to do, I'm going to develop a risk bound to the posterior itself. And then we are going to specialize to the context of variational inference. So right now there is no variational inference. So just a simple application of Fubini's theorem and Markov's inequality. There is nothing fancy here. We can show that with probability at least 1 minus psi, the Renyi divergence risk with respect to the posterior distribution. So this is the Renyi divergence, and we are simply integrating it with respect to the posterior distribution. So this is bounded above by this penalized loss evaluated at the posterior, plus some logarithmic terms that we can ignore. Now you might be wondering, how is this useful? Right? But the point we should keep in mind that this right-hand side is going to be minimized at the posterior. And if we plug in any probability measure here, that's going to serve as an upper bound. So we can try to come up with our own choice of this probability measure Q and try to make this upper bound as tight as possible. And that would essentially lead to an optimal risk bound. So let's try to see how we can do that. So the base risk with respect to the any divergence is bounded by this quantity that we have just shown. And let's look at the objective function one more time. So this is a loss, integrated loss with respect to this density Q plus a quantity, which is the KL divergence between Q and the prior pi. So this serves as a penalty, and this is essentially the loss. Now, how to actually make this small, make the sum of these two things small? Now, in order to make the first term small, we should choose Q such that Q assigns high probability around theta star in a small neighborhood, right? But in doing so, we'll make this term to be large because pi has no information on theta star. So if pi is allowed to be diffused, then this term is going to be larger. So there has to be something in between that kind of does the trade-off. And this is what we have come up with. So if we simply take our Q to be prior truncated to small neighborhoods around the theta star, then we can show that this quantity would be optimized. Okay? So now this observation alone will actually help us in determining the variational base and associated risk bounds. So what's the difference with the posterior analysis? In the posterior, we are minimizing over all probability distribution. So we are not going to do that in variational inference. So we are going to minimize the KL divergence over certain tractable family of probability measures. Okay, and this minimization is equivalent to minimizing the same objective over this gamma. Now this is almost trivial to obtain. What you do is just simply replace the posterior by the variational optimizer here, because you're not optimizing over the entire space of probability measures, but you're optimizing over gamma, which will give you the variational estimate here. And this is essentially the variational based risk, and we have an upper bound here. Okay. Now this upper bound is quite flexible in the sense that we are actually free to choose our Q theta. So we should choose our Q theta to make the upper bound to be as small as possible. And if it matches with the optimal risk, then we are done. So that's pretty much the idea. So again, going back to our intuition about finding the optimal Q theta, if we can actually take the Q theta to be of this particular form, the prior truncated to small neighborhoods around theta star, and if this Q theta happens to be within this tractable class of probability measure, then we can show that the objective function is optimized within the tractable family. And the value of the objective function at this family turns out, at this particular member of the family turns out to be this particular number. So as you can see, this is simply the log likelihood integrated over the prior inside the small neighborhood. And then we have a penalty, which comes out in terms of the log of the prior distribution around this neighborhood. So in practical problems, what you're going to come up with is upper bound to the negative log of the prior concentration of this neighborhood. So let's say in most practical problems, it would come up to be the prior concentration around a delta neighborhood would be e to the negative n, some function of delta, which we call epsilon delta. And then the first term, if we actually can choose the neighborhood to be of size delta, the first term can be shown to be bounded above by n delta square. So the objective function can be bounded above by n delta square plus n times epsilon as a function of delta. So the function would be changing from problem to problem. If we can solve this fixed point iteration, delta equals epsilon delta, that would actually allow us to optimize the upper bound. that would allow us to choose the desired epsilon, and that would, in most cases, what we have found can optimize the upper bound and deliver us the optimal risk. So let's look at an extension of this idea to the case of latent variables. When we actually have latent variables along with parameters, things get a little more complicated. So let's consider the case where we have observation yi and zi. These are mutually independent, and these zi's are discrete latent variables. Let's, for instance, think of the mixture model example. And we consider a mean field approximation, which assumes a product distribution over theta and the latent variables. Then you'll get a very similar type of analysis, except that the objective function will now consist of 3 different terms. So the integrated loss will be there, the KL divergence would be there, and there would be an additional term delta, which is the source of approximating the log marginal likelihood for a given value of theta from its variational approximation using the latent variables. Okay, so because of the presence of latent variables, we have this additional term, delta J. But that's not really a problem, because we know this delta J actually vanishes if we choose the QZI, or the variational family for ZI, the latent variables, to be the full conditional distribution that naturally appears in Bayesian inference. Okay, so if you choose the full conditional distribution as QZI, we can actually close this gap and actually get rid of this delta. And this actually gives us some idea of how to choose, how to actually optimize this objective function. Okay, so again, I'll probably skip the details and go directly to the main theorem. When we actually have latent variables, the variational base risk for the parameter of interest can be upper bounded by the objective function for any q theta and qzn, but the objective function is given by this expression, plus some logarithmic terms that we can ignore. So now our job would be to, in specific examples, to choose q theta and qzn such that the upper bound is optimized, right? And we kind of know how to choose qzn. We simply choose qzn to be the full conditional distribution, so that the delta term actually vanishes. Okay. So this is exactly the next slide. So if we actually choose QZI to be the corresponding full conditional distribution where theta is evaluated at theta star, and if you choose the Q for theta to be the prior truncated to a small neighborhood around theta star, the true value, then we can optimize the upper bound when we have latent variables. So let's try to see some examples just to kind of illustrate this idea. So I'll start with the basic example, which is low dimensional linear regression. So here the parameter of interest is simply the regression coefficient and the noise variance. We use a mean field approximation, and we solve the argmin to get our variational estimates. Okay. So what we can show that if the prior density is continuous and it assigns certain high probability around the true value, we can get an optimal risk of the order d log n over n. Okay, so this is not surprising at all, because ignoring the correlation between beta and sigma squared doesn't lead to any kind of loss in accuracy of the point estimators. Of course, we cannot recover the original posterior distribution, but at least the risk is of the right order. So we can extend this idea to the context of high dimensional sparse linear regression. So we are using a spike and slab prior here with Gaussian type of slab. And we use a block mean field family for our latent variables, which are the indicators here. and the beta j's, which are the regression coefficients here. So if we do not use a block mean family, we are going to get inconsistent estimates because the ZJs and beta Js are intimately related with each other. Okay, so this is the variational problem that we are solving. We are solving the arg mean between the corresponding tail divergence. And again, we can show that if the prior density is continuous and the prior assigns positive probability around beta star, and if the true beta star is S sparse, that means it has at most S many non-zero entries, then we can recover the optimal risk bound in the sense of S log n over n. So these results are not surprising at all. I mean, so you're using a prior which is continuous and has sufficient probability around the true parameter. So even if you assume in the posterior things are independent, you're going to get good point estimates. So now let's look at a different example. Let me take a question here. So I kind of glossed over the idea of thickness. So the word thick in this context means the following. So, so the prior distribution, in order for the posterior to be consistent, a natural condition is the prior should assign certain probability around small Kullback-Leibler neighborhoods around the true parameter. And this probability has to be of certain order in order for the posterior to be consistent. And we essentially need the same condition here for the variational posterior to be consistent at the true parameter. Okay, so does that answer the question? Okay, so let's look at another example where things actually go wrong. Okay, so this is a very popular example of linear Gaussian state space model, where we have the observations given, the state variables is drawn from a Gaussian distribution where B is the emission parameter and xt has a Markovian evolution where little a is the transmission parameter. Okay, and we have Gaussian prior on the emission and transmission parameter, and the variances are endowed with inverse gamma prior. Okay? And let's consider a mean field family of this particular form where we assume the state variables are independent with each other. Okay, so now this is a big assumption we are making. We know that they have a Gaussian evolution, but we want to see whether we can recover the risk bound if we assume independence in the latent variables. Okay. Now, with this assumption, you can actually show that if the true transmission variable is in 0 to 1, which is the right regime to look into, then the risk bound doesn't really converge to 0. So we have actually inconsistency. It actually is lower bounded by C. And this makes complete sense because in the posterior, we are dealing with n dependent variables, and ignoring the dependence in this n variables actually is a price in the sense that the posterior incurs an inconsistency in terms of the parameter of interest. Okay. Now, how to solve this problem? Well, simply don't assume the state variables to be independent in your variational approximation. So that's exactly what we have shown. If we simply consider this block mean field decomposition, where we assume that theta and the latent variables are independent, but the latent variables or the state variables are not independent among themselves, then we can show that the risk bound is of the optimal order. Okay? So I'll not go into the details, but essentially the risk bound is the number of parameters times log n over n, and that is exactly what we are able to achieve here. Now, we have to really pay a price here because assuming independence of the state variables allows us to use something called the coordinate ascent which is a very easy algorithm to implement. But here, since we are not using the state variables to be independent, we have to take advantage of belief propagation idea in order for the algorithm to proceed. Okay. All right, so let's try to kind of wrap up the discussion on statistical accuracy here. So the key findings are the following. So we must construct the likelihood and the prior in a way that the posterior is optimal. If the posterior is optimal, of course, there is no hope for the variational approximator to do a good job. Right? In order for the posterior to be optimal, we need the prior to be thick in the sense that I just described. That means it should have adequate mass around certain neighborhoods around the true parameter. And the variational family should consist of densities of this particular form. So this is something that we can check in practice. So if the variational family does consist of densities of this particular form, we can actually obtain optimal response. Okay. So let me take a question again. So are there convergence guarantees for belief propagation in the linear Gaussian state space models? Actually, yes, because the dependent structure is tree-like. So whenever the dependent structure is tree-like, there are nice guarantees for the belief propagation ideas. But if you go beyond tree-like dependence, then of course there are no guarantees. Okay, so again, just to kind of back up the discussion, so what really this means for mean field approximation, right? So whenever you are doing a mean field approximation, your family may not contain densities of this form because the neighborhood here is a Kullback-Leibler neighborhood, which may not contain a rectangular interval that will deliver the same prior concentration, right? So in order for a mean field approximation to be successful, we would really require this neighborhood, the Kullback-Leibler neighborhood, to contain a rectangular interval which has the same prior concentration order. Otherwise, the posterior is going to be, and the variational approximation is going to be inconsistent. And that exactly happened in the case of the linear Gaussian state space model, because we are trying to approximate a KL neighborhood of n many latent variables, which is like an ellipsoid, and we are trying to put a rectangle inside the ellipsoid. So there is a lot of mass which are left unaccounted for, which caused the variational to be inconsistent. Okay, so in the remaining 5 to 6 minutes, what I'll talk about is some of our recent results on the algorithmic convergence of the coordinate ascent, which is a very popular algorithm used for mean field variational family. Okay. So again, so right now we are essentially narrowing down our family to the mean field family. We are not operating within a general class of probability measure. So our mean field family is densities which are of this product form, and for which the KL divergence, of course, is finite. So depending on whether you use the previous values of the coordinates, you can have two versions of the coordinate ascent. One is the sequential CAVI, coordinate ascent variational inference, and the other one is parallel coordinate ascent. So basically what we are doing is you are updating one variable at a time, keeping all the other variables to be constant. And if we actually use the most updated value of the remaining variable, you get the sequential coordinate ascent. And if you update everything in a block, you'll get the parallel coordinate ascent. Okay. So this is the schematics of the two different types of coordinate ascents. So the parallel coordinate ascent updates everything in a block, and the sequential is doing it sequentially. Okay, so just to give some intuition, let us focus on the 2D case and the parallel coordinate ascent. Okay, so let's assume that Q1 star cross Q2 star is the global minima of the variational objective function, which is denoted by F. So since Q1 star and Q2 star are optimal, you get this internal coherence relation pretty easily, actually. And using this internal coherence relation, what you can come up with is the following. So the discrepancy of the objective function at an arbitrary Q1 and Q2 with the objective function at the optimal value is simply the sum of the individual objective function as if things are independent. And then there is a discrepancy term, which looks kind of like a covariance term. Okay. So it's an integral over Q1 minus Q1 star and Q2 minus Q2 star with the log posterior. Now you can clearly see that if in the posterior two variables are separable, then this delta term is really 0. But if there is some interaction term between two parameters in the posterior, this number, this delta n number is not going to be 0. And this delta really plays a critical role in making this problem a non-convex problem. Because if this delta is 0, it's basically KL divergence between univariate KL divergences, which is the convex problem. Okay, so just to kind of give you a flavor of the main result that we have, we define a generalized correlation by taking this delta n term, dividing it by appropriate weighted Kullback-Leibler divergence, and then taking supremum over the QJs, the probability measure. And we call it the generalized correlation. Right? So intuitively, it really captures the correlation, posterior correlation in some sense. So this is the main result that we have. If this generalized correlation, which is a function of the posterior distribution, is within 0 to 2, then for any initialization, the two-block parallel coordinate ascent is a contraction. Once you have a contraction in the KL divergence, you're going to get exponential convergence. Okay? Now, in many examples, you cannot really bound this generalized correlation by 2. But what you can achieve is local convergence. That means you can bound this generalized correlation locally around neighborhoods of the truth by 2. And in that case, if we do a suitable initialization within that neighborhood, you're going to get a contraction. Okay. So this generalized correlation really plays a critical role in guaranteeing that your coordinate ascent will converge to the global minimum. Okay. We have a similar result for the sequential coordinate ascent. And one thing that I really want to point out here, so these are all for 2 dimension, but if you want to extend everything to D dimension, you want your generalized correlation to actually scale down with respect to the dimension. So you would want your correlation to be between 0 to 2 over square root D minus 1 in order for your algorithm to be a contraction. Okay. Now, I'll conclude with one particular example that I really like. So what does this generalized correlation less than 2 over square root D minus 1 really mean in a particular application? Okay. So let's consider the very simple toy example where we have a multivariate Gaussian whose precision matrix has this equicorrelation form. Of course, we know that to maintain positive definiteness, we need the correlation to be between negative 1 over D minus 1 and 1. So if you do a mean field approximation to this Gaussian target, then the parallel coordinate ascent will essentially proceed as this linear system, essentially, okay? And you can verify, it's really easy to verify that the condition that this generalized correlation is less than 2 over square root d minus 1 is simply equivalent to having the absolute value less than 1 over d minus 1. Okay? Now, you might be wondering that there is a large range of parameters that we are missing out. So what happens when rho is greater than 1 over d minus 1? So in order to do that, in order to see whether our theory is really giving a sharp result or not, we analyze the dynamical system directly, and we can show that it actually converges for absolute value of rho being less than 1 over d minus 1 and diverges if rho is actually greater than 1 over d minus 1. So in that sense, our theory is giving sharp result. But even a more interesting fact that I'd like to point out is the sequential version actually converges over the entire range. And we are not able to manifest this using our theory. So our theory kind of treats the sequential and the parallel version similarly, and that's probably why we are getting this bottleneck. So right now, what we are analyzing is a common mitigation strategy in order to kind of enlarge our region of convergence. So this is by employing a retraction-like idea, which is very similar to the proximal gradient descent. So what we are doing is, in order to make a step to the t plus 1, we do not make a full move. Instead, what we do, we have a holding at the tth step with, it's our t plus 1th step is really a convex combination of our previous step and the direction that we would actually move if we are doing simple coordinate ascent inference. And this holding is achieved through this parameter eta. And we can show that if we choose eta to be small enough, then we can make the spectral radius of the dynamical system to be less than 1, and we can achieve convergence, even if rho is pretty large. So this is again a very common mitigation strategy in optimization. And right now what we are exploring is a generalization of this idea. We know that to the objective function, if we add this additional term, we are actually going to get updates which will look like a retraction. And what we have seen in practice, this retraction actually helps us enlarge the region of convergence in dimension which is larger than 1. And computationally, this is not too hard because one can get closed form updates for conditionally conjugate exponential family models. So with that, I'm going to conclude. So some recipe for algorithmic success in variational inference. We should try to avoid parallel coordinate ascent as much as possible, because what we have noticed is some kind of periodic or cyclical behavior. And also it has smaller radius of convergence. We should do sequential coordinate ascent, which is more popular, I believe, among practitioners. And also this new idea of proximal coordinate ascent, by adding this extra term with our objective function, might be useful in high dimensions. Okay. So that's pretty much it. Here are some references. So the red ones are for statistical accuracy, and the blue ones are for computational guarantees. I believe the talk would be posted, so you can look up the references. And that's probably, that's it. And thank you for your time. Thank you.
Great. Thank you, David. And any questions from the audience? So while the audience might be composing questions, I have a quick questions. And so it's really a very interesting talk. So can actually interpret this result basically explains like why the mean field mean field variation approximation is a good choice. It's like compared to a lot of different approaches. Like these are kind of, I kind of can see that, your result kind of justify that why mean field is actually a good choice. Can I really interpret that this way?
Yeah, I mean, from an algorithmic point of view, mean field actually allows us to do coordinate ascent, which is a very simple algorithm. But what we have seen from a statistical point of view, it doesn't really lead to a loss of accuracy if you are interested in just the point estimators. But of course, you cannot recover the entire posterior well. You have to pay a price somehow. Yeah. Thank you. Yeah.
Okay, great. Other questions? So actually, I have another question about, it's actually about the value alpha. So I noticed alpha variation of inference is kind of very clever idea. So I'm just curious, like how do people choose alpha in practice? Is it like generally like something we preserve, or we just choose it to be half because it has this connection with Hellinger distance?
Right. I mean, at this point, we are just exploring it as a theoretical tool. Practically, I won't recommend using it. But there is a nice piece of work by Peter Grunwald and co-authors, which actually does look into this choice of alpha in practice. What choice would actually lead you to robust inference? Because once you raise the likelihood to a fractional power, you are essentially making your likelihood a little bit flatter, right? So, I mean, in case of model misspecification, that might prove to be a little more helpful in practice. But a good choice of alpha, we have to look into their work. But at this point, we are just using it as a theoretical tool, just to better understand things.
Okay, great. And so Marina has raised the hand. So I'm now allowing Marina to speak. Marina, you should be able to speak now.
Yes, thank you. Thank you for the interesting talk. And I wanted to ask the following. Back like long time ago, of course, when people did mean fields or other variational inference, by default, it was the likelihood that was more peaked and the prior that was flat. And so essentially Q would fit the likelihood. Whereas now you're advocating the opposite. You're advocating that we kind of fit, like choose Q based on the prior essentially. And I would like to see if you can give us an intuition about what are the advantages or disadvantages of this?
Right, I think it's really a great point. So again, the choice of Q that we have in the talk is prior truncated to a small region, small neighborhood around theta star. That simplifies a lot of our analysis. So if you choose your Q to be just a probability measure, which has a small variance around the point theta star, that would work too. But you know what happens is that if you choose your Q to be exactly the prior truncated to the small neighborhood, then you can actually work out the objective function in a nice way. But you're right, you do not have to choose your Q based on your prior. So just because there is some cancellations with the KL divergence, I have chosen it like that.
Yes, I see.
But that's a really good point.
Thank you.
Okay, great. Other questions for the speaker? It's Friday afternoons and approximately Friday nights. I think people are probably eager to enjoy that night.
Yeah.
Okay. So if no other question, then thanks the speaker again, and thank you so much for this really great talk. It's very inspiring.
Thank you, Jens.
Okay. Thanks. Thank you, everyone.
Thank you.
Thanks, everyone. Bye.
Here.
Bye.